Yeah, good afternoon, everyone. For those who don't know me, my name is Wang. I'm a lead R&D engineer at ISO New England. I also have part-time roles at UT San Antonio and Harvard University. I'm also the secretary for this task force. So for the work I'm going to present today, it's mostly from my responsibility at UT San Antonio. And still, my industry background at ISO New England also contributed a lot for shaping the directions of the research. So let me get started. The title of my talk is Limitation of PMU Data for High-Frequency Oscillations. So before I get started, I want to acknowledge the sponsorship by Department of Energy, especially from their EERE CETO office under the Optima project. So we have a very strong team. So without them, this work cannot be achieved, especially my PhD student at UT San Antonio, Mr. Bowen O. He has been leading this effort. And also we have bi-weekly meetings discussing with Slava from ISO New England, Han Chao from GE Vernova, and Jim from PNL. We also had a conversation with Wenpeng Yu from ISO New England to help us under some PMU fundamentals. This work was motivated by an effort like 5 years ago when I was at NREL to investigate the 18 to 20 hertz oscillation event in Kauai Island as a team. This work was also inspired by Professor Wilson Xu's interharmonics work he presented last year. There was a paper we completed, which is under review right now. We have the preprint available online from archive. So a couple of slides on the background. So PMU phasor memory unit have been there for 2 or 3 decades now, and a lot of real-time, online or offline PMU applications have been developed to improve the situational awareness. So NASP collected inputs from the industry summarizing the PMU applications. Interested audience can look at the second reference there for more details. And it has been proven that PMUs have been a very useful tool for monitoring and analyzing the electromechanical dynamics, which is usually below 3 to 5 hertz. And but there are also 2 well-known issues with PMU for capturing oscillations, which are reported as well. The first is the aliencing effect, which is caused by the insufficient reporting rate that limit or mislead the observed dynamics. So there was an earlier work by Chitian from Dominion Energy and Luigi from RPI that reporting that there was a 22 hertz oscillation event happened in Dominion Energy, which appeared as 8 hertz oscillations by PMU data. So that was a very typical aliencing effect. And the second issue is the low-pass filter attenuation. So PNL's report, the last reference on this page, showing that for dynamics above 5 hertz, it'll be distorted by the PMU. So high-frequency oscillations, these are not new, dynamics. In the past, we already have sub-super synchronous oscillations in the past. For example, there was a sub-synchronous oscillation event in Russia in 2009 from a hydro power plant, which unfortunately killed like 70 plus people. But nowadays, the subsynchronous oscillations are emerging from the increasing inverter-based resources and data centers. For example, the 23 Hertz large load oscillations in ERCOT and the 18 to 20 Hertz oscillation from Kauai Island. The second reference on this page show was a technical paper by the IEEP's IBR SSO task force summarizing the real-world SSO events. So, so two figures in this slide, just to give you a feeling about what the high-frequency oscillations will look like. This is a 14.7 Hertz oscillation event observed in Dominion Energy territory. And the left-hand side is a time domain response of the voltage magnitude. And the right-hand side is the frequency spectrum. And you can, from the right-hand side figure, you can see that the problem is showing up on the right-hand side, which is around 14.7 Hertz. That's way beyond what PMU can deal with. How to monitor high-frequency oscillations? So based on existing infrastructure, we have SCADA, we have PMU-based WAM system. Those are like streaming data into the control center. And we also have digital fault recorder doing high-speed measurements at substation level locally, with or mostly without streaming to the control center. So from the system operator point of view, so how can we analyze high-frequency oscillations based on what we have? So most likely, before we have those high-speed data streamed to our control center, we have to utilize whatever, being the best, which is currently the PMU-based WAM system. So, and we know that there are two well-known issues with PMU for high-frequency oscillation. But the question is, if we resolve those two well-known issues, can PMU phasor or PMU data accurately capture high-frequency oscillations? So that is exactly the question we are trying to answer in our research. First, think about what algorithm or what is the process in PMU. So especially the phasor estimation algorithm. If you look at the commercial PMU products, so the DFT-based algorithms are the dominant method in most commercial PMUs. And we know that PMU is definitely not the only method for phasor estimation, but it is the predominantly used one so far. And there are the reasons for that, because DFT directly estimate the fundamental frequency. It's very efficient computation-wise. It's well understood and standardized. It aligns very well with the IEEC 37.118 performance requirement. And so in short, historically and practically, the DFT-based phasor estimation is the industry standard. We know that other phasor estimation methods can also be used in some, such as least square, Prony, matrix pencil, common filter, and etc. But those are not covered in this study. So we are focusing on DFT-based phasor estimation in this talk. But similar study, if a PMU is using another algorithm, similar studies should always be, conducted to verify that their accuracy and their effectiveness when dealing with high frequency oscillations. So here, let's take a look at how PMU calculates phasor. What is the internal process? So where's my laser point? Okay. So once we get the waveforms from the transducer, it's gonna pass through an analog digital converter module, and along with a low pass filter, usually 3,000 samples per second or 15,000 samples per second. And then we got the point of wave data. So those are waveform, like sinusoidal. Then we apply the DFT, discrete Fourier transform, to convert that point of wave data into phasors. And then the phasors will pass through a low pass filter, a second low pass filter here, which typically has a cutoff frequency at 60 Hertz. And then that filtered phasors will be time-stamped and reported as the PMU data that we see in the field. So theoretically speaking, we can, do the phasor calculation at each, once a new point of wave data sample comes in, and then report a new phasor. But that's not the most effective way. It consumes a lot of computing power. So I think somehow people found a sweet spot, which is 30 samples per second or 60 samples per second, adopted in the field. So the two well-known issues happened in the later stage here. The second low-pass filter will distort the phasor, and then the low reporting rate will cause the aliasing effect. Those are well-known. So those are not the focus of this talk. So this talk will try to figure out if there is any distortion caused by the DFT algorithm when converting the point of wave data into the phasor data. If so, how much? And this presentation will try to briefly clarify a term, which is the oscillation frequency in the next slide. And then I'll try to answer this question with numerical examples. And after that, I'll try to show analytically why is that. And then I will show some implications and also some initial effort that how we can deal with this. So on this slide, I'm trying to just to clarify the definition of oscillation frequency. I know everybody probably know what is oscillation frequency, but sometimes it can be confusing because we have data from different sources. So the physical voltage and current signals are 60 Hertz, right? And because the 60 Hertz waveforms, as shown as the red curves in the two plots on the top, they are kind of boring. And what is interesting is the variations in their magnitude and in their phase. So that's why we condensed all those information into phasors and only communicate those phasor information to the control center. If you look at the first column here, the first plot is showing the time domain behavior of the 2 Hertz oscillation modulated in the magnitude. And the second plot is the frequency spectrum of the waveform data, which is the red curve here. And third plot is the frequency spectrum of the phasor data, which is the blue curve right here. So the oscillation frequency we are talking about in most of the cases is the frequency in the phasor using phasor data. which is the 2 Hertz here. And if you look at the frequency spectrum of point of wave data, you have a 60 Hertz, which is the frequency of our power system. And you see a subsynchronous component, 2 Hertz, below that fundamental frequency, which is 58 Hertz here. And we also have another frequency component, 2 Hertz above. So the 3 plots here in the same column represent the same behavior of the system, but in different domain, time domain and frequency domain. But if you look at different data source, you may see different, frequency components. So right now it's totally fine because most of the oscillation monitoring applications are based on PMU. So there is not much confusion. But in future, if we start to use the waveform data, and that's gonna cause quite some confusions. So I would say the best practice is to specify what data we're talking about when we say the oscillations. Are we talking about in the phasor domain, or are we talking about the point of wave? So let me show the first example here, a numerical test. So we consider a 2 Hertz oscillation modulated in the amplitude of a sinusoidal waveform. And we assign a 5% oscillation amplitude here. And then we apply a typical PMU, DFT-based PMU algorithm. 1 cycle DFT, reporting 30 samples per second. And you're gonna have the result on the right-hand side. So the red curve is the waveform, the original sinusoidal waveform. The blue curve, you probably cannot see it here because it's covered by other curves. The blue curve is the modulated 2 Hertz oscillation curve. And that is the ground truth I used when generating this signal. And then if you apply the 1 cycle DFT, you got the phasor curve, which is the pink curve that you cannot see, but it's close to the other curves. And then after the low pass filter, you got the green curve. You probably can see a little bit here. And then you downsample that green curve, you got the black dot right here. So this is a 2 Hertz low frequency oscillation, and DFT algorithm works pretty well, and that is well known. So if we do the same thing, but to a 40 Hertz oscillation, you're gonna see quite surprising results here. So going from the blue curve, which is the ground truth of the modulated oscillation, if you calculate the DFT phasor, you got the pink curve. And you can notice that there is a big difference between the blue curve and the pink curve. And that one was caused by the DFT algorithm. So basically, to this point, we already shown that, at least numerically, the DFT-based phasor does not accurately represent the high-frequency oscillations. And further, we can also just take a quick look at the following process to verify the impact from the later blocks of the PMU process. So if you go from the output from DFT, the second low-pass filter will generate the result shown in as the green curve. So you can also clearly see a difference between the pink curve and the green curve. So that distortion is caused by the second low-pass filter. And going from the green curve to the black curve, and that's the downsampling process. So you can see that the like 40 hertz oscillations appear to be a 10 hertz in the PMU output. That is totally caused by the aliasing effect or low sampling rate, low reporting rate issue. So in short, DFT is not good for high frequency oscillations. Then we're gonna analyze this analytically. So starting from a signal with modulated oscillation in the amplitude, here we try to apply a n-cycle DFT, just try to make it general. And given a time window here, so right now we assume that the time tag is at the center of the window. So later on we'll show why this is the choice. If we do that, so we apply the Fourier transform, we get the real and the imaginary part of the phasor. So then with quite some derivation effort, we can reach this point, this expression. So I skipped all the detailed derivation steps, but interested reader can look at our paper, which contains a lot of details about how did we derive this. So given this, what do we learn? So let's compare with the original signal we designed. So we have the amplitude A, that's the amplitude of the fundamental frequency component, and we have the modulated oscillations. If you compare, you see that we have an extra term in the oscillation amplitude, and we have one extra term. Sorry. So the first term, I call it DFT measurement gain, because in the original signal, it's like there's, if we really put a number there, it has to be 1, right? But now we have an expression here that may not necessarily be 1. So, but this expression, if you look at it, it has three factors or 3 parameters that can determine its value. The fundamental frequency F1, the oscillation frequency FOS, and the DFT window length N. And if you look at the detailed expression, the first one is a rational fraction, and the second and the third one, if you put them together, it's actually a sinc function, the sine, like cardinal function. We'll analyze that in detail later. And the third term, another introduced term is the right term here. I call it remainder or repo term. It actually introduced some components at second, third, and higher harmonics of the oscillation frequency, but with very small amplitude. So right now, for this study, this is not the focus. But those components may affect other process. But for this talk, it's simply ignored. So let's see what implications do we have once we have that expression. First of all, what is our goal? Our goal is trying to measure the oscillation components as accurately as possible. Basically, we want the F gain to be 1. So we don't want it to change anything. Just give me whatever it is, right? But that's the goal. That's the ideal case. In reality, this is true, or this is almost true, when the oscillation frequency is very low. When it's much lower than the fundamental frequency, or when the oscillation frequency is close to 0, for example, below 3 to 5 hertz, the electromechanical oscillations. For that, we can try to derive this, and find some approximations of it. For example, those two terms will become very close to zeros. And the last term is a sinc function. If the input is 0, then the whole thing will be 1. So that's the definition or the property of sinc function. So with that, we can see that the gain function is almost 1 when the frequency is very low. And then if the oscillation frequency increases, the gain will deviate very significantly from 1. So it is very difficult to show analytically, and we're going to show numerically about this function in the next few slides. And that will tell us how the magnitude will be attenuated. And what surprised is this could also result in a possible phase flip, and that's something new we discovered in this study. So to detail the two effects by the DFT algorithm, the first one is the attenuation. So when so I think that is what we're going to show in the next few slides. So I'm going to on this slide I'm going to talk about the second point, the phase flip phenomenon. So by phase flip, I mean that the oscillation phase could be shifted by 180 degrees compared to the ground truth. So how can we interpret this? So f gain function has a sine component in there, right? If you think about the input to the sine function, if the input is greater than pi and less than 2 pi, the sine function will be a negative value, right? Will have a negative value. And the negative value, if you plug that in into the f gain will be a negative value. And when you think about the expression in the original signal here, m should always be a positive value to represent amplitude, And how do we turn negative value to a positive value? We change the cosine function by adding a pi, offset there, and then minus f gain will become positive to meaningfully represent the amplitude. So that's why we have a 180-degree difference in the oscillation phase. So how would this happen? How do we make the input to the sine function to become pi or go over pi? So usually if we increase n, the whole value will more easily approach pi. Or if we increase the oscillation frequency, this term will approach pi as well. That will cause the possible phase flip. So phase flip is very possible for high frequency oscillations, but we assume that the oscillation frequency is still below 60 Hertz. For oscillations above 60 Hertz, I think that will require additional investigations. For sure, there will be phase flips, but they'll be a little bit more complicated because we have to take into consideration the first term, the rational fraction here. So for example, if n, the window length, DFT window length, times the oscillation frequency, if the product is above 60 Hertz but below 120 Hertz, so you can multiply all sides by the same factor, which is pi over f1. f1 is the fundamental frequency. You'll have this expression to be between pi and 2 pi, and then you have sine this thing to be a negative value, and then you have f gain being negative, and that will cause a phase flip. So next I'm going to show a numerical example. So the same 40 Hertz oscillation, but this time instead of using a 1-cycle DFT, now I'm using a 2-cycle DFT. So in this case, n equals 2. And then from the expression, we can calculate a number that is around negative 0.2, which means the magnitude of the oscillation estimated by the DFT phasor is 20% of the true value. If you look at the figure, you can see that the pink curve is much lower than the ground truth, which is a blue curve. And we also, predicted from that expression, we're going to have a 180-degree phase shift. And you can tell from the figure that the pink curve is out of phase with the blue curve. So the 40 Hertz oscillation observed by this DFT phasor is significantly misleading. The magnitude is attenuated and the phase is flipped. That doesn't represent the true information in the system. So next 2 slides will show what is the impact of the 2 important factors of the f-gain function. One is the DFT window length, which is n here. So if we try different n values from 1-cycle DFT all the way to 6-cycle DFT, we're going to draw the f-gain function versus the oscillation frequency, FOS. You can see that for 1-cycle DFT, the f-gain decreases slowly with the oscillation frequency, and it reaches 0 at 60 Hertz. For 2-cycle DFT, f-gain reaches zeros at 30 Hertz. 3-cycle, 20 Hertz. 4-cycle, 15 Hertz. 5-cycle, 12 Hertz. 6-cycle, 10 Hertz. So basically a longer DFT window, although we know that it's usually for better noise resistance, but at the same time, it can increase the attenuation in the estimated phasor. It will lower the detectable oscillation frequency. It will result in a higher risk of phase flip. So basically, the DFT window length design matters. Now here we introduce the new concept called phase flip frequency, which is at this frequency, the f-gain function will become 0. So next slide, basically the same information, but represented in a different way. So here we put everything in a table format. For example, this number here, 90%. It means that if we apply a 3-cycle DFT to estimate oscillations, a 5 Hertz oscillation, we're gonna have, we'll only be able to capture 90% of the magnitude of this 5 Hertz oscillation component. Basically, we lost like 10%. That will be a 10% error in the oscillation amplitude. So represented by the red line here. So if you look at this blue line, at the phase flip frequency, that's equivalent to like 100% error. So basically, if you don't choose your DFT window carefully, the oscillations in the waveforms can be completely invisible in your PMU data. And another information we can tell from the table is that the P class, the protection class PMU, usually, typically using like 1 or 2 cycles of data for DFT phasor calculation. They capture the oscillation much better than the M class, the Merriman class PMUs. which usually rely on like 2 to 6 cycles of data. So previously we talked about the DFT algorithm's impact on the phasor amplitude. And we found that DFT has an impact on the phasor amplitude. And at the same time, it can introduce phase flip, basically yes or no, whether there is a 180-degree shift in the oscillation phase. And we haven't, shown whether DFT will introduce any impact on the oscillation phase directly. So here, this slide will show that. So given this signal here, we apply the n-cycle DFT, we got the result. This is exactly what we did, but this time we didn't assume the timestamp. We still use tau here. And we rewrite the expression, and then we compare the derived phasor with the original modulated components there. And we can find that if we let t be the whole thing here, then we'll have the phase exactly the same. The two expressions will be exactly the same. If not, if we don't pick the center, this whole thing, which is the center of the DFT window, the two phase will be different. So we should let them be the same, right? And that's then here's an example to show that if we don't use that choice, if we pick the ending time of the window as the timestamp, what will happen? So that is shown by the black curve here. So where you can see a constant phase shift compared to the ground truth, which is represented by the blue curve here. So when we look at the IEEE standard 637.118 published in 2011, it recommended T-center, which is the middle instance of the window, to be used as the time tag of the phasor. So basically, we don't have to worry about the impact from DFT on oscillation phase. I mean, direct impact. There's nothing to worry about in this sense. So now we're done with the analytical investigation. And we know that our investigation is limited to the amplitude modulation. We haven't tried, phase modulation in the original analytical signal. That will be something that we can extend in future work. And also, all the work conducted so far are like theoretical. We would like to verify that by hardware PMUs. But what we learned is very clear. The DFT-based PMU phasors cannot accurately capture high-frequency oscillations. So with that, the next question is what to do if we know DFT is not good for high frequency. So next, I'm going to show some initial efforts we did to move on this topic. So before going forward, one thing I want to remind everyone is the PMU phasors are not the original information of the system. They are the derived quantities. The original or the raw data from the system would be the original physical quantities, which is the current and voltage waveforms. So then let's take a look at what the waveforms look like. So we used PSCAD simulation to generate some waveforms on a 9-bus system where we have 1 grid following and 2 grid forming inverters. We simulate 3 cases. The first one, we trip the line to excite a low frequency oscillation. In the second and third cases, we intentionally increased the PIL gains to generate some high frequency oscillations. We use a 2 kilohertz sampling rate to collect the phase A voltage waveforms from bus 2 right here. The first row here are the time domain behavior. The second row represents the frequency domain. I'm sorry that the figures are very small here. You probably cannot tell very clearly, but what I really want to tell is that the sub and super synchronous frequency components, especially for high frequency oscillation cases, they are not equal in amplitude. And phasor concept, not just DFT phasor, the phasor concept may not be able to capture that. And the phasor concept may not be a well-defined concept anymore. So we don't know. So that's the question here. And next, we proposed a new signal model to better represent the information in the waveform. And we also propose a 5-step estimation method to figure out the 8 parameters in the signal model. So I probably should skip the details, and maybe we can come back in the discussion session. So basically, this 5-step estimation method can reliably estimate those 8 parameters, and then we can compare with the original waveforms. And then we can define an error expression. So basically, the error is defined as the sum of squared point-wise error averaged over a time window, then normalized by the amplitude of the fundamental frequency and put it in a percentage unit. So here's an example. If we consider a 40 Hertz oscillation and consider equal amplitude in the sub and super frequency component, because we know that in this case, the waveform signal is phasor representable. In that case, we can draw the phasor curve. Otherwise, there's no way to define a phasor, at least currently. So we test on this signal. We use DFT algorithm to define a phasor or calculate a phasor curve, which is shown by the blue curve here. And we also try our 5-step estimation method. Then we got the black curve, which is on top of the red curve. The red curve is the reference. And we find that the 5-step method and the new signal model give us a better representation of the waveform information there. The DFT phasor will lose 9% of the information. So then we apply the 5-step method on the 3 oscillation cases we got from the EMT simulation. And we get the result in the table. Basically, the DFT method will generate much higher error than the proposed method. The proposed method still doesn't give us a 0 or close to 0 error. This is mostly, we believe this is mostly due to the nonlinearity or other harmonics, or some harmonics in the signal that are not captured by our signal model. So questions for future work. Are the power system oscillation waveform signals phasor representable? And this is something we don't know. If not, or when it's not, what is the best signal model? And how to adapt existing PMU-based oscillation analysis applications to these new signal models. So these are the questions that I guess should be answered before, in order to better deal with high frequency oscillations. And here's the key findings and conclusions. So PMU data are good for low frequency oscillations, but not good for high frequency ones. And the DFT algorithm can introduce significant amplitude attenuation and the possible phase flip. Even though we resolved the two well-known issues, we still have this problem coming from the DFT algorithm. And the DFT induced distortion will increase with the oscillation frequency and the DFT window length. And what we learned is that M-class PMU are more prone to attenuations and phase flips than the P-class. And even with the adequate reporting rate and the properly designed low-pass filter, the DFT algorithm itself fundamentally limits the accuracy of DFT phasors. So what's the practical impact? And why does this matter? Because the emerging sub and super synchronous oscillations may be underestimated when F gain function is below 0, right? And DFT phasor may contain a phase flip in there that can mislead oscillation analysis applications. For example, the oscillation source location, which largely rely on the oscillation phase information there. For high frequency oscillation studies, what do? We should either like use point of wave data. If the phasor data is available, the limitation must be considered explicitly. And in future, we need for more deployment and utilization of waveform measurement equipment like the digital fault recorders. And we need to improve our phasor estimation algorithms. And then we need to revisit the definition of phasor concept and whether it's still applied to power system high frequency oscillation signals. And maybe we also need to propose new signal models to better represent high frequency oscillations and adapt existing applications to those new models. And with that, I conclude my talk and ready for questions and discussions.